So, let me now define another entity that we need to consider various kinds of structures that a polyhedron can have. So, now here let me define a direction of a I am doing it for a polyhedron, direction of a polyhedron, and here I will do it for this particular one. So, I will take it for the I will take up the polyhedron that corresponds to the feasible region of a linear programming problem that we defined in 3, which I have been calling as LPP3. Okay. So, here you have Ax equal to b, x greater than or equal to 0, and of course, x belongs to Rn. So, this is my polyhedron in dimension, and we say that a vector d belonging to Rn is said to be a direction of the above polyhedron if AD is equal to 0, Ax equal to b. So, AD must be 0 and D non-negative. All components of D are non-negative and D satisfies the condition that AD is 0. Fine. So, now you see what do we mean by this? The idea is the direction. The idea is that if I take any, so let x naught belong to F. Remember, I am calling the feasible region, that means all x which satisfy this condition and the non-negativity condition, they are the collection of all these feasible solutions I am referring to as F. So, if x naught belongs to F, then x naught plus lambda d belongs to F for all lambda non-negative. Yes, because if you take A of x naught plus lambda d, then A of x naught plus lambda a d, but a d is 0. So, A x naught will be equal to b, and since all components of d are non-negative, lambda is something positive, non-negative, all the components here are also non-negative. That means, for any lambda positive, this is also feasible. This is also a feasible solution, and so that means that I can continue proceeding in the feasible region, because as lambda goes becomes higher and higher, this vector also becomes of a length higher and higher, and so I continue to remain in the feasible region no matter what the value of lambda is, as long as it is non-negative, it is a positive number. Okay. So, this is the idea, that means you can move in the feasible region along a direction, right. Now, of course, you can have your description of the polyhedron as less than or equal to b or greater than or equal to b, but then this I will leave as an exercise for you to sit down, and of course, I will demonstrate through this particular example to show you the concept of a direction and how do you go about locating it. Fine. So, now see, for example, if you have this polyhedron. So, and then another thing is that if a polyhedron has a direction, then it cannot be bounded, right. Okay. So, what I am trying to say is that so maybe presence of a direction in a polyhedron implies that the set is not bounded, because I will not be able to find, since no m greater than 0 exists such that x naught plus lambda d norm is less than m for all lambda greater than or equal to 0. Yeah, because you give me a m, I will be able to, I will choose a value of lambda higher than what it is right now, and then violate this inequality. So, the set is not bounded. So, the presence of directions imply that your feasible region or your polyhedron is not bounded. Okay. So, let us look at this example here. Now, since I do not have all equalities, of course, I could convert it to standard form and then talk about, but I want to demonstrate that how you can modify this definition when you have when all the constraints are not inequality or of equality type. Okay. So, here that means to find a direction for the given polyhedron, D has to D, which is D1, D2, D3. Okay, remember I will write it as a row vector, does not matter, but I understand it's a 3 tuple. Okay. So, D this given polynomial, to find the direction for this should satisfy So, here it will be, for example, minus D1 plus D2 equal to 4. Now, for this one it will have to be D1 minus 2 D2 plus D3 less than or equal to 0. Sorry, I am sorry, this is 0. Yeah, because obviously, since I want this constraint to be satisfied for all values of lambda is less. So, if it is less than or equal to 0, this condition will remain feasible. So, just check it out for yourself, and then here it will be that D3 is greater than or equal to 0. Yes, and of course, D1, D2, D3 are greater than 0. So, I would like you to sit down and just make sure that these conditions are enough to define a direction. That means, what you, of course, I am assuming non-negativity. So, all you need to verify is that for all values of lambda, such a point, for all values of non-negative values of lambda, this point will remain feasible. So, please do this exercise for yourself. Okay. So, now here you want to look at this, and let us see what will be the yes. So, if you want me to, let me draw the thing for you. Okay. So, this is 1, this is 2, and this is the third axis. Then you have D. This implies that D2 is D1. Yes, and so here that gives you this thing here. This is the line D2 equal to D1, right? Now, yes, add these two, fine, yeah, because this one has given me D1 is equal to D2. Yes, yes, I should have done it this way. No, I don't need to write this. Yes, okay. See, from here D1 is equal to D2. So, if you put D1 as D2, this gives you minus D2 plus D3 is less than or equal to 0. Okay, right. So, this says that D3, this implies D3 is less than or equal to D2. Okay. So, the set of directions that we have finally obtained is all D1, D2, D3, where these components are non-negative, and D1 is equal to D2, and D2 together are greater than or equal to D3. So, this is a set, right? And so, you see that the I have marked with the arrow the region in which any direction would satisfy this condition, and so therefore, this becomes a cone. You see, it is a cone of all the directions, with any vector lying in the direction in that arrow region would be direction for the set, right. And now, I am also talking about extreme directions, just like we have the concept of extreme points. So, here you see 1 comma 0 upon root 2 would be a unit direction. It is also a direction, because see here D3 becomes 0 and D1 and D2 both are 1. Similarly, because you can have D2 and D1 both greater than or equal to D3. So, you can also have the direction 1 comma 1 comma 1 divided by root 3. and so I have marked those two directions. So, then any direction, and that they form the direction, the two sides, extreme sides of the cone, and any direction in this cone would be then be a direction of the feasible region, right. And so, I have shown you that you take a non-negative combination and C1 plus C2 comma C1 plus C2 comma C2, right, and this would be because C1 C2 are non-negative. So, these satisfy the condition that D1, the first component and the second component are the same, and they are both greater than or equal to the third component. So, therefore, you see that the feasible region that we were considering is not bounded, because there are directions in the feasible region. So, now let us continue with some more results of the for the simplex algorithm. That means, I am trying to develop the theory. Yeah, the thing is that we have so far, let me now say something about the geometry and the algebra that is running parallel. See, I first defined for the LPP 3 that I am calling, I had the problem as minimize C transpose x subject to Ax equal to Bx greater than or equal to 0, right. So, I define your feasible region F as x belongs to Rn such that Ax is equal to B, x greater than or equal to 0, and I call this the set of feasible regions. Then I showed you that if F is non-empty, then it will always, and then of course, we define the concept of a basic feasible solution, and I showed you that if F is non-empty, that means if F has a feasible solution, then it will always have a basic feasible solution. So, this basic feasible solution came through the idea of selecting m linearly independent columns here, then we call that as a basis, and then I put the remaining variables as 0, and I solved the reduced system, and I got a. So, this was a completely algebraic concept, right. Then I have also been looking at F as a polyhedron, F as a polyhedron, right, because F is being described as intersection of a finite number of hyperplanes and a finite number of half spaces. So, this becomes a polyhedron, and then I have defined an extreme point of F also, because F is a polyhedron. So, what I am trying to say is that on one hand we talked of basic feasible solutions that form part of the feasible solutions, which are all collected in F, and then I have also looked upon F as a polyhedron, and then we have the notion of an extreme point of F. So, now in the result that we are going to prove shortly, I want to show you that these two notions, even though they have been defined separately, are actually one and the same. That means, a basic. So, let me write down this theorem here. Yes, I am not going into the technicalities of, because if you define a polyhedron, then you talk of a dimension. So, here of course, since these are all equalities, so the dimension of this polyhedron in particular is n minus m, because I am assuming that rank A is m. So, therefore, the dimension of F is as a polyhedron is n minus m, and so one can have a representation for F in which you only require n minus m variables, but we are not discussing that here. My basic idea is that we want to show you that this concept of a basic feasible solution and an extreme point are one and the same. So, theorem is that corresponding to a basic feasible solution x bar belonging to F, there is an extreme point. Now, actually, again I should not be saying that there is an extreme point. A basic feasible solution is an extreme point and vice versa. Basically, this is what you want to show. So, corresponding to a basic feasible solution x bar belonging to f, there is an extreme point. So, when I say there is an extreme point, that means when I am looking upon f as a polyhedron, maybe in a smaller dimension, the corresponding dimension of f. So, corresponding to a basic feasible solution x bar belonging to f, there is an extreme point and vice versa. Maybe I should reword the theorem. Essentially, what I want to say is that if and only if it is an extreme point. Okay, so maybe you will allow me to rewrite the theorem. I will just erase this. Okay. X bar belonging to f is a basic feasible solution of f if and only if it is an extreme point. It is an extreme point of f. This is a better way of what I want to say. What I said earlier is also correct, but then we would have to be more technical. So, I want to just give you the basic result here. That is, x bar is a basic feasible solution of f if only if it is an extreme point of f. Start proving the theorem. I will of course take the definitions. So, here if you look at the proof, so x bar is a basic feasible solution. So, consider x bar belonging to f is a basic feasible solution. This implies that a x bar is equal to b, x bar greater than or equal to 0, and sigma a I x I bar, I varying from 1 to r, is equal to b, where after renumbering the columns of A, I have made the first r variables as the positive ones. Okay, so x bar is a basic feasible solution. It may be degenerate, I do not know, but so what we are saying is that if the r components of x bar are positive, then I renumber my columns, as I have been saying it earlier. I renumber the columns, and the first r columns then correspond to the positive components of x bar, right. Suppose x bar is not an extreme point. This implies there exist x1 and x2 belonging to f such that x bar can be written as lambda x1 plus 1 minus lambda x2 for 0 less than or equal to lambda less than or equal to 1. See, my definition of an extreme point is that it cannot be expressed as a convex combination of any other 2 points of the set. So, I start with a basic feasible solution, then I am saying that suppose it is not an extreme point, then I must be able to find 2 points x1 and x2 in f such that x bar can be expressed as a convex combination of these 2 points, right. Fine. Now, the thing is that xi bar is 0 for I varying from r plus 1 to n. Remember, I have renumbered the columns and the variables. So, my first r components of x bar are positive, the remaining n minus r are zeros, which means that x bar I is 0 for I varying from r plus 1 to n. Now, since lambda is greater than or equal to 0, x1 and x2 are also non-negative. What do you get from this equation? You see, this is 0 here for any component of x bar, which is after from r plus 1 to n, for any such component. Here if you, because this is component wise sum, so here everything is non-negative. So when can this equation be satisfied? This will be satisfied. So this implies that x1I equal to x2I are 0 for I varying from r plus 1 to n. That means the last n minus r components of x1 and x2 must also be 0. Otherwise, this equation will not be satisfied. We are starting with the assumption that x bar is not an extreme point. So, I can find x1 and x2 such that x bar is expressible as a convex combination of these 2 points. But then since the last n minus r components of x bar I are 0, it implies that the last n minus r components of x1 and x2 must also be 0, right. Okay. So, therefore, b x bar b, we are referring to the first r components, is equal to b x1 b is equal to b x2 b is equal to b, because both x1 and x2 are solutions to your they are in the feasible region. So, they must be satisfying these equations. The last n minus r components of x1 and x2 are 0. So, the system reduces to bxb bar, right, where b is the basis, where b is the, oh okay, yeah, there is a little problem here in the sense that b, I am assuming only r components positive. So, let us say that we have extended the basis, where b is the extended basis, is the extended basis for x bar. Okay. I have explained this concept also to you, that if you have a set of linearly independent columns which is less than the basis size, then you can always add few more columns to it so that it becomes a basis. So, b is the extended basis. So, then I have this equation which implies that x b1 is equal to b inverse b is x b2, and this is equal to x b1, right. And since the last n minus r components of the 3 vectors are the same, so this implies is that x1 equal to x2 is equal to x bar. And so, our assumption that x bar is not an extreme point fails, right, because I have shown you that if you start with this assumption, then you have no choice but to say that, but to conclude that x1 and x2 have to be x bar. So, therefore, x bar cannot be an extreme point. So, I started with a basic feasible solution, and I have shown you that x bar also has to be an extreme point. So, now we do the other way, which I started writing earlier. Okay. So, now the if part, that is, if x bar is an extreme point, the extreme point of, maybe I draw a line here, the extreme point of f, it is also a basic feasible solution. Okay. So, now here we will say that x bar is an extreme point, and I will again say the same thing, that yes. So, x bar is an extreme point, and it is in f. So, therefore, Ax bar is b, x bar is greater than or equal to 0, and suppose x bar is not a basic feasible solution. And remember, our definition of a basic feasible solution is that the columns corresponding to the positive variables in a feasible solution, if they are linearly independent, then I can always call it a basic feasible solution. So, suppose x bar is not a basic feasible solution, this implies that summation yi ai, I varying from 1 to r is 0. So, here again I am assuming that I have renumbered the columns just as there. So, the first R columns correspond to the positive components of x bar, and so the corresponding columns are linearly dependent, right. This all yi's are 0, at least some, right. Okay. Then I do the same trick, I multiply this by theta and add here. So, if you write this in expanded form, it will be a1 x1 bar and so on. So, without working out the details, so I will say that okay, 1 and this is 2. So, 1 plus theta into 2 imply that summation xi bar plus theta yi ai, I varying from 1 to r, is equal to b. See, I am trying to show you, I am trying to, so here the idea would be, I have started with the assumption that x bar is an extreme point, and now I want to show that it is a basic feasible solution. So, I will try to show you that if x bar is an extreme point, then x bar has to be a basic feasible solution, and since I am starting with the assumption that x bar is not a basic feasible solution, therefore, I will have this. So, using this I will try to contradict the fact that x bar is an extreme point, and so since I have assumed this, this is given to me, that means I should be then able to say that x bar has to be a basic feasible solution. So, this will be the idea behind the proof, right, by contradiction, as you say, I am proving the result by contradiction. So, this is this. Now, let us see, yi's can be positive, negative or zeros, right. Now, if and I am taking theta, yeah, here I should have said for theta positive, let me take, or no, okay, nothing, I am not saying anything, okay, yes, it is on second thoughts. So, this is, I have this now here. Now, consider all yi's greater than 0. So, for all yi's, then I should, my theta, there will be a limit on theta, because I want xi bar plus theta yi greater than or equal to 0. So, that means what we are saying is this is non-negative, this is positive, this is positive. So, if theta is positive, then no problem, but I am trying to find out how far can theta go as a negative number. So, this is this implies theta has to be greater than or equal to minus xi bar upon yi, which is a negative number, right, because this is positive, this is positive. So, this is the negative number. So, let me take theta to be this thing as max of minus xi bar upon yi, because if I take this as max, yi greater than 0. So, among all yi's which are positive, I am taking this ratio, corresponding ratio here, and then choosing the maximum. So, if theta bar, so if theta is bigger than this theta bar, then you see the corresponding numbers here will all remain non-negative. Yes, if my theta is bigger than theta bar, then it will satisfy all these inequalities, and so the corresponding number here will remain non-negative, and this is what I want to ensure, right. So, let us continue with this proof here. So, theta bar, you see, if I choose theta greater than this, then I am okay, because these numbers will not become negative. Similarly, for all yi less than 0, xi bar plus theta yi greater than or equal to 0 will imply that theta, see here yi is negative. So, when I write the inequality theta yi greater than minus xi bar, and then when I divide by yi, it is a negative number. So, the inequality will reverse, implies theta should be less than or equal to minus xi bar upon yi. Yeah, for all yi negative, in order that this number remains non-negative, I should have theta satisfy this condition, which means that if I choose theta bar as a number which is minimum of minus xi bar upon yi less than 0. Again, now this is a positive number, right? And once my theta, if my theta is greater than, see this is less than or equal to. So, if theta is less than theta upper bar, then all these numbers will remain non-negative. So, here theta bar we selected theta bar as this, and your theta lower bar was max minus xi bar yi with yi greater than 0, right. So, we chose this, and then the idea here is, you see, if I draw this line here, this number theta lower bar, because yi is positive, xi is also positive. So, this number will be negative. So, your theta lower bar, therefore, this number is 0 here, and this is theta lower bar, and theta upper bar is somewhere here, because theta bar is a positive number, yi is less than 0, right. Now, the thing is that I want to satisfy both the conditions, because for whatever the value of yi, positive or negative, my components here should be non-negative, right. So, therefore, for example, if theta bar is less than theta upper bar, theta lower bar, then I will choose this interval, right, and I will call it. So, therefore, right, and if theta bar upper bar is smaller than this, then I will accordingly choose an interval around 0. So, that this interval is a subset of the interval theta lower bar, theta upper bar. The whole idea is to, so therefore, what I am saying is that select theta naught as minimum of this, right. So, then for and you can now verify because of this diagram. So, like this, then for 0 less than or equal to theta less than theta naught, the two vectors x bar plus theta y and x bar minus theta y are feasible, okay, for your LPP3. That is what we have been discussing, right. They are both in F. So, now if I choose a theta which is in this interval, then x bar plus theta y, and or maybe just to be safe, we will take it to be strictly less than theta naught, does not matter. So, then these two solutions are feasible, right, and x bar can be written as half x bar plus theta y plus half x bar minus theta y. So, that means I started with the assumption that x bar is a extreme point of F, and then I have been able to construct, and then with the assumption that x bar is not a basic feasible solution, I could construct two feasible solutions such that their convex combination is your point x bar, which contradicts the fact that x bar is, because we started with the assumption that x bar is an extreme point, right. So, this contradicts the fact that x bar is an extreme point. Therefore, our assumption that the columns corresponding to positive components x bar are linearly dependent is not correct. Okay. Fine. And so, the columns corresponding to positive components of x bar are linearly independent, and if they are m in number, fine, because then x bar is a basic feasible solution. Otherwise, we will extend. So, if necessary, extend this set of columns, Okay, set of linearly independent columns to form a basis P. So, we have seen this process so many times that in case you have a feasible solution and the corresponding and the columns corresponding to positive components are linearly independent, then we can always say that it is a basic feasible solution, because we can extend the set of linearly independent columns to form a basis, and then it becomes a basic feasible solution by our definition. So, this is what so therefore, the theorem is complete now, because I have now shown you that there is 1-1 correspondence between a basic feasible solution. Well, 1-1 in the sense that if a feasible solution is there which is a basic feasible solution, then I can show that it must be an extreme point and vice versa. But we have also seen that when you have degenerate basic feasible solutions or a degenerate extreme point, then there can be more than one basic feasible solution corresponding to the same extreme point. Okay. So, this is what, and now let me in continuation of this only show you discuss one of the pathological cases. So, before that I will like to, so a pathological case, let me just say this way. So, here so far we have defined it for equality constraints with non-negative variables. Remember our definition of a basic feasible solution. So, now suppose consider the system of constraints well, what shall I say, dx plus E y equal to b, okay, where and where x as this is greater than or equal to 0, and what we are saying is that d is m by n1 and E is m by n2, n1 plus n2 is equal to n. So, the total number of variables are n, but you have first n1 variables satisfying the non-negativity constraints, the second set of variables, the n2 variable, these are not are free, right. So, now obviously the definition of a basic feasible solution will change, though again you can, and what I am going to do will tell you how to always reduce a system. I have also discussed it earlier with you that if you have unrestricted variables, you can always convert them, the system, to a restricted except that the dimension goes up. Like, okay, anyway, so here I will just straight away define the this thing for, so a basic feasible solution. So, we will say that x y is a basic feasible solution of 1 if the set of columns dj such that xj greater than 0 union all columns ei I varying from 1 to n1. That means all columns, these are linearly independent. Okay. So, that means for the unrestricted variables, the corresponding columns all must be linearly independent, and here for the positive components of the x, the corresponding columns. So, all these together should be linearly independent. This is the definition, right. Now, if you look at the so now look at the equation or the constraint x1 minus x2 equal to 1, let us say x1 x2 belonging to R2, right. Consider this feasible region. Okay. Consider this feasible region. Now, if you draw it in the R2 plane, this is x1 x2, then this is passing through the point 1 0 and 0 minus 1. and this line x. So, the feasible region is this line which is extending to both the directions to infinity in both the directions, right. So, no extreme point, right. No extreme point. So, you can see it from geometry, but if you apply this definition, or not, there is no but, and if you apply this definition, this gets verified, because here remember you are in R2, there is only one constraint. So, what are the columns, and there are no xj variables, in the sense that no non-negativity constraint variables are here, both the variables are free to take any value. So, in this case your columns are 1 and -1, these are the two columns, it is one dimensional. So, your m is 1, so therefore, this is one column in this. So, these are linearly dependent, because one can be written as minus, or this can be written as minus times this. So, these two columns are linearly dependent, therefore, there will be no extreme point to this feasible region, as we have as it can be verified by the definition also. So, I will transform this region, which is a straight line extending to both sides, and hence therefore, has no extreme points by this transformation. So, x1 gets replaced by x1 plus minus x1 minus, x2 gets replaced by x2 plus minus x2 minus, and all these four variables are non-negative, right. So, this is the new constraint now. So, I have embedded this two-dimensional thing into a four-dimensional region, right. Now, you see, since single constraint, so the rank of the coefficient matrix is again 1. So, I will again have a basic feasible solution corresponding to one column, and a singleton non-zero vector is a linearly independent vector. That is what I am using here. I should have said this set is linearly independent, that is okay. So, then column A1 corresponding to this, if I choose, then I will put all these 3 equal to 0, and my solution would be 1 0 0 0, right. So, this is the basic feasible solution. Similarly, here because of non-negativity I cannot choose these. So, I will choose this one. So, if I choose A4 as my basic column, then I will put the first 3 variables to 0, and then that will give me x2 minus as equal to 1. So, this will be the corresponding basic feasible solution. They are distinct basic feasible solutions, and hence there are 2 extreme points to this system. So, you see, by the non-negativity constraints on the variables are necessary for the theorem to be valid. The theorem that I was talking to you about, correspondence between a basic feasible solution and an extreme point. So, here you have because of non-negativity on the variables, you could then find out 2 basic feasible solutions, and hence there are 2 extreme points. So, this was the thing. Now, another word of caution that is needed here is that the correspondence is not 1-1. That means, the theorem or the lemma that I wrote in the beginning, that I proved to you, showing correspondence between basic feasible solutions and extreme points. So, here you see, if a degenerate basic feasible solution is there, then you can have more than one basis corresponding to the same degenerate basic feasible solution. So, to think that you will have and therefore, there may be more than one basis which is giving you the same basic feasible solution, and hence the same extreme point, right. So, therefore, this is I thought I will, through an example, I would show you this. So, look at this example, and here you have 5 variables, all are non-negative, non-negativity constraints are there. So, now I wrote out this thing column here, and I choose the basis B1 as A1, A2, A3, or okay, maybe I did the row operations here, and finally, I reduced the matrix to this form. So, you see, you can read from here. Okay, I could have made zeros here also, but that would not make a difference to the basic feasible solution, because this is 0. So, when I subtract this from here and twice this from here, these numbers will not change. So, that is why I did not do that arithmetic. So, here you can read from here anyway. So, this is a set of linearly independent columns, 3 independent columns, and so they form a basis, and the corresponding basic feasible solution is phi 1 0 0 0, right. And so, there is an extreme point also, corresponding extreme point in R5, which will be given by this. But then you see from here, from this tableau, that if I replace, I can remove drop A3 from my basis, and then I can take A5, because A4 again is linearly dependent on A1 and A2, right, because there is a 0 here. So, therefore, A5 is the other column, which together with A1 and A2 will make a linearly independent set, and so this forms a basis. And see, because there is a 0 here. So, even if when you pivot on this, you see if you pivot on this, you will divide by -2. So, it becomes a 1. This will not change, and again when you make zeros here, these numbers will also not change. So, trying to show you that when you have a degenerate basic feasible solution, there is not a unique basis which corresponds to the basic feasible solution. So, therefore, B1 and B2 give you the same basic feasible solution, and hence the extreme point will also not change, because right, because your basis your basic feasible solution has not changed, the corresponding bases have changed. So, in the lemma I said that corresponding to a basic feasible solution there will be an extreme point, but then when you talk of a basic feasible solution, you have a concept of a basis corresponding to it. So, essentially what I am saying here is that there can be more than one basis corresponding to the same extreme point under degeneracy. So, the correspondence will be 1 1 only if you have non-degenerate basic feasible solution, then the corresponding extreme point will also be non-degenerate, and therefore, that correspondence will be 1 1. So, essentially I could I had told you that there is an upper bound on the this would be NCM, right, out of, that means if the rank of the matrix A is M, then you choose M columns for forming a basis, and so the number of basic feasible solutions that you have, the upper bound will be NCM, because out of the n columns you want to choose m columns, and hopefully, I mean if they are linearly independent, then of course they form a basis, but then again having a basis may not always lead you to a basic feasible solution. I have gone through all this with you, but in any case this is an upper bound on the number of basic feasible solution, or the number of bases that you can have, and therefore, this is also an upper bound on the number of basic feasible solutions you can have, and therefore, we also said that this is also an upper bound on the number of extreme points that you can have. So, this is the kind of count, and I just wanted to caution you that the correspondence, we have to understand what we mean by this correspondence, and essentially I am trying to say that under degeneracy there can be more than one basis which will correspond to the same extreme point.